Okay, hello APC Mechanics students. So we are now in class 9, section 2.1, resistive forces, part 1. Then let me start. So this section 1, resistive forces. Bodies in motion may be submitted to frictional forces. Previously we have discussed kinetic friction, which is the friction due to a moving body. Although kinetic friction is considered to be a variable force, but however, if we're considering a specific dynamical system in which the normal push in this case is set to be constant, and we know that the coefficient is constant, then we can say or claim that in this specific system, the frictional force, which is the kinetic friction, is constant. And this is considered as a first approximation. To better model such system, we introduce resistive forces of the type. So F is given by minus kV and F is given minus kV square, where K is a positive constant. Here we notice that the force is directly proportional to the velocity, and we know that as the body is moving, the velocity changes, which makes the frictional forces here in this case non-constant forces, so they are variable forces. The minus sign indicates that such forces opposes the motion. And we say in magnitude that F is given by kV or F is given by kV square. Now, section number 2, falling body and the drag force. Okay, previously we have discussed the dynamics and kinematics of an object in a free fall with no resistance. Now we are interested in studying an object from rest left freely to fall due to gravity and submitted to frictional forces that are variable given by minus kV due to a resistance. Now we're gonna only consider the case where F is minus kV and not V square, where K is a positive constant. As the object starts falling, it will be submitted to a variable frictional force known as the drag force. Now here, as we can notice from the animation, let me repeat it, that this is the frictional force, which is the drag force due to a resistance. It is varying, it is increasing as the velocity is increasing. So we say the drag force increases exponentially until it is balanced by the pull of gravity and eventually reaching the terminal velocity. Now, later on through this section, I will refer to what is meant by the exponential increase and the terminal velocity. But now let's keep in mind, as the object is falling, the force due to a resistance, which is the drag force, it's a non-constant force and it's gonna increase with the increase in velocity. Now we are interested in the following notion: to determine the differential equation that governs the variation of V. The solution of this differential equation, to discuss the acceleration and the terminal velocity, dimensional analysis, and the descriptive and analytical kinematics in which they will reflect the exponential increase and decrease of different variables. Then let's kick things off by starting with the differential equation of V. Now, differential equations are equations relating the variable and its derivatives. Such equations are obtained by big laws, and whenever we say a big law, until this moment we only have one law that produces dynamics, which is basically Newton's second law. Now consider an object of mass m falling under gravity and submitted to frictional forces due to a resistance, as we have mentioned previously, and this force is given by the drag force, given by F is minus kV. Now this is the falling object, and these represent the drag force. Now what are the forces acting on the object? The object has a mass, it will be subjected to the pull of gravity. We have the drag force, which is up. And here we're gonna represent the FPD of the falling object. Now if you consider the initial state at which t is equal to 0, what are the forces acting on the falling object? We have the pull of gravity, which is down, and as we've mentioned, we have the drag force, which is up. Now, but why I have represented the drag force, which is capital F to V0, to be 0? Because the object is left to fall freely, and if it's left to fall freely, then the initial velocity is given by 0, and we know that the force is given by minus kV, so that would be minus k multiplied by 0, which is 0. Then initially, because the initial velocity is 0, Till this moment or momentarily, the drag force is switched off. Now in the transient state, as the object starts to gain some velocity due to the pull of gravity, the resistive force, which is the drag force, is gonna increase. So that would be the transient state. And finally, reaching something called the steady state. Now notice that in all three FBDs, the pull of gravity is constant because G is considered to be constant. But at the steady state, the drag force will be balanced by the pull of gravity, and in this case the falling object will reach a velocity known as the exiting velocity or the terminal velocity. Now in order to determine the differential equation, I will consider only one FBDs, which is the transient state, and in this case we have two forces, the pull of gravity and the drag force, such that the drag force in magnitude is less than the pull of gravity. And now we're gonna apply Newton's second law for the falling object. Now we have the pull of gravity and the drag force. We need to project this equation because this is a vector equation. I'm gonna consider the vertical direction, and down is positive. Then in this case the pull of gravity is gonna be positive because it's down, and for the drag force it's gonna have a minus sign. And remember always that the acceleration has no projections, no positive or negative projections. Now the pull of gravity is being replaced by mg, and the resistive force would be replaced by its magnitude, which is given by kv. Now notice that here we have two variables given by v and a, and no other equation can be implemented for a simultaneous solution. Then the way to proceed is to convert this equation into a differential one. Now, because we are determining the differential equation of v, so we need to convert a, the acceleration, into a velocity, and this can be done easily using calculus. We realize that v and a are related by a is dv by dt. Then replacing a in the above equation, we're gonna get mg minus kv is equal to m dv by dt. And now if we move this term to the other side and we flip the equation, we're gonna have the following. And now if we divide everything by m, this cancels with that, and we're left with the following differential equation. And we say that this is a first order differential equation in v. Why this is a first order? Because the derivative is a single derivative, not a double derivative. The solution of the differential equation. The differential equation that governs the variation of v is given by that, has the following solution, which is expressed in terms of exponential function. So let me recall that mg is the pull of gravity, k is a positive constant, and this is the exponential function. Now, how can we make sure that this is the correct solution of the given differential equation? The above solution must reflect the physics of the problem. This can be tested and verified by testing limiting values. So what are the limiting cases that we're talking about? We know that initially the velocity has a zero value, and it's gonna reach a terminal velocity which is considered to be constant because, as we said previously, that the forces are balanced. Let's verify this from the solution. So let's replace t by 0. So I replaced here t by 0, then we're gonna have e to the power minus k over m multiplied by 0, which is e to the power of 0. And we know that e to the power of 0 is 1, then 1 minus 1 would give us 0, and indeed this is verified. Now, what about the terminal constant velocity? We don't know specifically what is the time bound or the time limit until which this object reaches the terminal velocity. So the best that we can do, we can take the limit as t approaches to infinity, and this can be applied to the solution that we have. Then, as I'm saying that the terminal velocity is attained after an infinite relative amount of time, that is t is infinity. Now we're gonna replace time by infinity as we see here. Now this is a positive number multiplied by infinity, and here we have a negative, so it's gonna be minus infinity. And we know that by definition or from the graphical analysis of the exponential function, e to the power minus infinity is gonna be 0. Which means that the terminal velocity would be gm divided by k, which is basically a constant, and that is verified. Now, what about the acceleration and the terminal velocity again? Now, since we have an explicit expression of the velocity, the acceleration simply can be determined using the calculus formula dv by dt. Now, let me walk you through the different steps. I have replaced the expression of v given by that. Now we need to derive this. This is a constant, can be dragged out. And I have expanded, I didn't take this out. I expanded this with this term and this term, knowing that there are several different ways in order to differentiate. Now here we have two terms. This is gonna be 0. And we're left with this. This is a constant, can be dragged out. And this includes time, and we know that the derivative of the exponential function is given by u prime eu. Then u here in this case is given minus k over mt, and u prime is given minus k over m. Then this term will be multiplied here. Then the minus signs will cancel, and here we're left with this multiplied by k over m, e minus k over m multiplied by t. Notice that this m with this m, k and k, they cancel. And we're left with an expression for the acceleration given by that. Now, as we said previously, that this acceleration must reflect the physics of the problem, and this can be done by considering the limiting cases. Initially, the acceleration is only due to gravity, and we need to check this. Now, if we replace time by 0, that would be e to the power something multiplied by 0, which is e to the power 0, which is 1. 1 multiplied by g is definitely g. Then that's verified. Now, at the steady state, the moment we reach the terminal velocity, forces is gonna be balanced. Balanced forces, it means that the state of motion is conserved. The object is not accelerating anymore, so we expect that the acceleration is gonna be 0. So let's consider that case in which t tends to infinity. Now e to the power minus infinity, so because k over m is a positive constant multiplied by infinity, that would be minus infinity. E power minus infinity is eventually 0. That means 0 acceleration, because 0 multiplied by g is 0. Then it's verified. Now, what about the terminal velocity? We've mentioned that the terminal velocity is given by v is equal to mg over k. And eventually, we can determine this expression again by consider the FBD at the steady state. Now, at the steady state, we know that the pull of gravity is being balanced by F. So we can safely say that F is Fg balanced forces. F is kV and Fg is mg. And here in this case, we're solving for v. Then v again would be mg divided by k. Then the terminal velocity is given by mg divided by k, which is the same expression we have determined previously. Then remember that we have two approaches in such type of problems in order to determine the terminal velocity. Either we consider from this, if we have the solution, which is the function v of t, we can take the limiting case in which t tends to infinity. This is one. Two, to consider the FBD at the terminal velocity. In this case, we have two balanced forces given by Fg and F. We can equate them and solve for v. Now, what about the dimensional analysis? Dimensional analysis, dimension means unit. And there is one quantity that in which we don't know its unit, and this is given by k. Then we are interested in doing dimensional analysis for k. Now, in order to determine the unit of k, it's sufficient just to put any formula that include k, any equation. The one which is straightforward is given by F is minus kv, and we can ignore the minus sign. And k would be represented by force over velocity. We know that the force is mass times acceleration. The unit of mass is kilogram, the unit of acceleration is meter per second square, and the unit of velocity is meter per second. And in this case, meters and meters, they cancel. We can cancel this second with this second, then we're left with kilogram per second. Then the unit of k is given by kilogram per second. Now, what about the descriptive and the analytical kinematics? The velocity is given by the following expression. Remember that we started from zero initial velocity. The velocity started increasing, reaching a terminal velocity or a steady state given by mg divided by k. We expect that the graphing of such a function would be like this: a zero initial velocity, asymptotic value given by mg divided by k. So we say this is an exponentially growing function, increasing function starting from zero and reaching a steady state of asymptotic value limiting speed given by mg divided by k. Basically, such type of functions are exponentially growing function and they reach a steady state. The coefficient which is out given by the asymptotic value. Now, what about the acceleration? The expression of the acceleration is given by that. Let's consider the limiting cases. Initially, the acceleration is given by g, and the final value for the acceleration is given by 0. Then in this case, we expect that the shape of the curve would be something like this, a decaying exponential function. This is an exponential decaying function decreasing starting from g and reaching a 0 value. Now, let's see the following problem, which reflect the type of problems that you might face on your APC paper. An object of mass m is dropped from rest near the surface of Earth. It's submitted to a resistive force given by kV, where k is a positive constant. Now here they didn't mention the negative sign because they're talking about the magnitude. So we should mention here it is a resistive force of magnitude given by F is kV, where k is a positive constant. Part A, we need to derive the differential equation that governs the variation of V. Then let's do that. We know that differential equations are obtained from big laws like Newton's second law. Now, in order to resolve Newton's second law, we need to consider the forces acting on the object. Now, I considered the transient state. We have the pull of gravity, which is down. We have the drag force, which is up. And here we're going to apply Newton's second law. We have Fg plus F is equal to ma. We need to consider a direction in order to project this vectorial equation. Down is positive, let's consider. Then it would be Fg minus F is ma. Fg is mg, F is kv. And here we notice that we have two variables given by v and a. We need to determine a differential equation that governs v. For this reason, we're going to switch a into dv by dt. Rearranging the equation, taking this to the other side and dividing by m, we would have a first order differential equation that governs the variation of v. Now in part B, they gave us the solution of the differential equation. So now we know much about this solution. That would be the terminal speed. This is an exponential function that has limiting values. For 0, that would be 1, and 1 minus 1 is 0. And as t tends to infinity, that would decay to 0, leaving us with the terminal velocity. Determine using two different methods the terminal velocity v terminal of the object. The first one is considering the limiting cases of the solution, and the terminal velocity is attained as t tends to infinity. Then v terminal would be v as t tends to infinity. We're gonna replace time by infinity. That would be, this is a positive constant, so e power minus infinity. That would be, this is gonna approach 0, 1 minus 0, and the terminal velocity is given by mg over k. Now the second method is to consider the steady state and to realize that the forces are balanced. Now here I replaced Fg by mg and F by kv, and we're searching for v. In this case, this is the terminal. So the terminal velocity is gonna be mg divided by k. So for both methods, we have the same answer. Now we need to determine the expression of the acceleration. The expression of the acceleration can be determined using calculus. Now we're gonna expand this. Now this is a constant, its derivative with respect to time would be 0. This is a constant, will be dragged out. Okay, and remember that we have derived this previously, and the expression of the acceleration after we do the cancellation is given by g multiplied by the exponential decay factor. Then the acceleration is given by that. Using idea 2, we need to calculate the initial and the final acceleration. So this is straightforward. We need to replace time by 0 and take, for the final, we're gonna take t tends to infinity. Then the initial acceleration would be e to the power 0, which is basically 1, and that would be g. And as t tends to infinity, remember that near the surface of the Earth, g is given by 9.81 meter per second square, which is a unit of acceleration. And as t tends to infinity, that would be e to the power minus infinity, which is basically 0. Then that's it for me in this video, guys. See you soon in a new one.